Hello, my name is Yong-Du John. My presentation topic today is extraction of oxygen-enriched air from water through vapor bubble deposition. I'm going to go over some research background related physics that includes Henry's law on solubility, Fick's law of diffusion, and the vapor pressure of water with which water may start changing its phase, followed by experimental work descriptions. Results are presented and analyzed based on the mass balance of oxygen and nitrogen gas species, and finally the conclusion is given. My topic today is on the dissolved gas and its extraction through a process of so-called degassing. It has long been the interest from scuba divers whether human beings can breathe underwater like a fish or insects like diving bell spiders. Another related issue is the oxygen concentration of the extracted dissolved gas mixture, which is believed to be about 34% as shown in the figure, which is higher than the normal atmosphere. According to an interview with Tech Insider, Neil Pollock, the research director of the Diverse Alert Network, pointed out three major issues to be solved for underwater breathing. First, we need to extract enough oxygen from water. Second, we should be able to store it in a container of some kind. The third, we need to make it breathable. The present topic can be said to be related to these issues to some extent. Methodology-wise, the aeration process used in food, beverage, and energy industry is a well-established process to extract dissolved gas from liquids. However, the conventional process equipment is large in scale and high energy consuming one. The principle of the aeration is based on the diffusion between the gas dissolved droplets and pure steam, and between steam bubbles and the gas containing liquid. What we want to declare is that a higher oxygen content air can be obtained by extracting dissolved gas in water. To accomplish this, we propose a new energy-efficient degassing process based on vapor bubble diffusion, which is characterized by the diffusion through micro vapor bubbles generated under lower pressure along with a 12-volt DC-powered microbubble generator. Also, in the present study, we attempt to measure the achievable amount of extracted gas and the oxygen concentration of the extracted gas. Related physical phenomena include Henry's law on solubility, fixed law of diffusion and the behavior of vapor pressure of water with respect to temperature. Bubble size and its dynamics are also important to estimate diffusion rate, but is not dealt in depth in the present study. Henry's law relates the solubility with the partial pressure of species with a proportionality constant called Henry's constant. For water at 25 degrees Celsius, Henry's constant for some important gases like oxygen, nitrogen, and carbon dioxide are shown in the table. Using the Henry's law, the mass of dissolved gas species are readily calculated. The presented calculation process shows how to obtain the concentration of oxygen and nitrogen gases considering the humidity contribution. Under an equilibrium condition with a standard air composition, 8.32 mg per liter for oxygen and 13.89 mg per liter for nitrogen are expected to exist in water in dissolved form. The volume fraction of oxygen then be 34.4%. For the solubility is a function of temperature, we may need to consider the effect of temperature as shown in the figure. It is necessary to have a low enough environmental pressure to generate vapor, and the vapor generated underwater will take the form of bubbles. In order to generate the vapor bubbles, depressurization is a helping step to arrive at vapor pressure of water at a given temperature. With the depressurization, the required additional pressure drop through the microbubbler can be minimized. Fick's law governs the diffusion of mass under concentration gradient, and thus same concept is applied for bubble diffusion with modification, in which concentration difference between the phase replaces the concentration gradient with a new proportionality constant called mass transfer coefficient. As the bubble size diminishes, the surface area of bubbles increases, and also the residence time of bubbles underwater may increase. Figure 5 illustrates the test apparatus used for the present study. It is composed of sealed water tank with gas collector inside and two large observing windows. The pressure inside the stainless steel cased tank can be controlled down to less than 0.1 atm. For the present study, we lower the tank pressure by vacuuming out the air inside and generate vapor bubbles through micro vapor bubble generator. The vapor bubbles rise up and are collected under the gas collector hood. The volume is measured using a scale on the scale on the hood under atmospheric pressure, and the oxygen concentration is measured to be stored for future analysis. Measurements are done using a DA100 Yokogawa data acquisition system, which records oxygen, dissolved oxygen level, temperature, pressure, etc. For a correct volume measurement, a millimeter scale is attached on one of the slant surface of the gas collector hood. A correlation is established between the water level on the scale and the captured gas volume using both a CAD tool and the actual measurements. This diagram shows a brief testing process. We divided the test cases into two parts. The first one is the result when there is only depressurization. The level of depressurization in the present study is limited by the vacuum generator used, and it was possible to lower down the tank pressure to 0.1 atm. Our test results show that at 57 minutes after depressurization, about 1.94 liter of degassing is achieved under a depressurized condition, which then shrinks to 0.199 liters when the environmental pressure restores to atmospheric pressure. It was found through the present study that the bubble generation is limited and also be the degassing. The photo illustrates the water level inside the hood at the end period of depressurization, that is 11.8 centimeter. The second test results are obtained for the combined process of depressurization along with micro vapor bubble generation. In this case, massive tiny vapor bubbles are generated with higher degassing rates. Due to the limited holding capacity of gas collector hood, this degassing process is repeated total of 5 times. The sum of total collected gas volume reached 5.89 liters at atmospheric pressure, and the oxygen concentration of the gas reached as high as 31.9%. Measured average oxygen concentration is found to be 29.9%. In order to interpret the experimental results, simple numerical simulation is conducted with parameters of initial DO concentrations and in terms of the temperature, water temperature. In the present study, the measured DO level is 18.6%. The water temperature is 17 degrees Celsius. In terms of total extracted gas volume, the measured volume at 17 degrees Celsius under 1 atm, once converted to 25 degrees Celsius at 1 atm, gives very close value against the expected value of 6.04 liters. Now, in terms of oxygen concentration of the extracted gas, the volume averaged oxygen concentration of 29.9% and the maximum of 31.9% is obtained, while the theoretical model predicts 31.4%, which shows again a very good agreement. Gas stripping based on vapor bubble diffusion is proposed, and the extraction of dissolved gas from water with volume and concentration measurement is experimentally conducted for water for demonstration. Through the present study, the possible limit of extractable amount of dissolved gas in water and the oxygen concentration of the extracted gas mixture is successfully identified through the experiment. Vapor bubble diffusion provides a simple and low-cost solution for the aeration, which will find many and diversified applications. Thank you.